Hi, I'm Kevin Lam from the University of Saskatchewan, here to give this short talk on our paper, More Errors versus Longer Commands, the effects of repetition and reduced expressiveness on input interpretation error, learning, and effort. Written with my co-authors Carl, Madison, and Andy, this paper presents our contributions to understanding how error reduction techniques can aid in improving a user's performance when using a noisy input mechanism. People interact with computer systems through an input mechanism such as a mouse and keyboard. These input mechanisms receive real-world analog signals as input from the user that the computer must interpret and convert into a digital format that the computer can recognize and use to execute commands. However, many signal-based input mechanisms share a problem when it comes to interpreting an analog signal: noise. The presence of noise can obscure useful information and make it difficult for the computer system to correctly interpret the user's intended input, which may lead to interpretation errors. Interpretation errors occur when the system interprets the user's intended command incorrectly. These errors often result in one of three types: misinterpretations, where the wrong command is selected; false negatives, where the user enters an input but the computer fails to recognize a command; and false positives, where the system executes a command without the user inputting anything. As a result of noise and interpretation errors, users are more likely to make errors themselves, be less satisfied with using the input mechanism, and have reduced performance overall. Our previous work in understanding the effects of interpretation error on user learning found that increasing rates of interpretation error can interfere with a user's ability to learn and effectively use an input mechanism. This translates to worse memorization of commands and slower completion times for selection-based tasks as the rate of interpretation error increases. While many researchers have looked into reducing interpretation errors, few have considered using techniques that improve the strength of the input signal to make it easier for the system to produce correct interpretations. We adapted two common techniques for improving signals from telecommunications: signal repetition and reduction of expressiveness. Signal or command repetition repeats the input multiple times, which increases the chance that the correct input will be interpreted by the system. On the other hand, reducing expressiveness decreases the number of states that can be interpreted from a single input. Thus, each input is given a larger interpretation space that the system can interpret from. We formed 4 research questions to test whether using these error reduction techniques would have an unreasonable impact on the user's performance. In other words, how would the increased command length from repeating a single command or using a longer command affect performance and perceived effort? Would these effects persist once the user becomes experienced with using these commands to perform selection-based tasks? How do these two techniques compare with each other? And since these techniques don't completely remove all errors, how does the residual error affect the user when using these techniques? We conducted a user study where participants were tasked with selecting items from a menu using the I, J, K, and L keys. A system was created where they were presented a list of target items on the left side of the screen. Participants were given a guide in the middle of the screen that showed the sequence they needed to press to select an item. After making a selection, it would appear on the right side of the screen. Participants would need to then compare their selections with the target list to ensure that they matched and no interpretation errors had occurred. If an error did occur, they would need to make a correction before moving on to the next item. Participants completed 10 blocks of training with 6 targets each. During these blocks, participants were measured for their task completion times, their command entry times, and the rate of user errors. Following the training blocks, the participants also completed a memory test that measured how accurately they could recall the command sequences from memory. We gathered data from a total of 171 participants throughout 7 different conditions. The first condition had selections made with sequences that were 2 keys long, with 4 possible items per key input, I, J, K, L. This condition had a 10% error rate per keystroke and was used as our baseline condition for input mechanisms that are used in noisy conditions. The second condition of 2 item 0% tests the expressiveness reduction technique by decreasing the number of possible items per key to 2, but increasing the sequence length to 4 so that the number of selections remained the same. This condition was tested under an error rate of 0%. 3 of the conditions tested the technique of command repetition, in which the key sequences were similar to the baseline, but the sequence was repeated once. In other words, if the sequence was JK, the participants would have to press JK to make the selection. These 3 conditions were tested at 0%, 2%, and 4% residual error rates. We also tested a variant of the command repetition technique, where instead of repeating the full sequence twice, each key was repeated twice. Again, if the original sequence was JK, the repeated sequence in this condition was JJKK. This condition was simply tested at a 0% error rate. Finally, the triple sequence condition was similar to the double sequence ones, but this time the participants had to repeat the command 3 times to select an item. We tested this at 0% to see if further increasing sequence length would impact the user's performance. From our results, we found that 2 item 0%, double sequence 0%, and double key 0% had faster completion times in training than the baseline condition of 4 item 10%. Conversely, double sequence 4% and triple sequence 0% were slower than the baseline on average. However, by the final training block, all error reduction techniques were as fast as the baseline conditions, and the double sequence 0% condition was still much faster. When looking at the user error rate during the training blocks, no differences were found between any of the error reducing conditions and the baseline condition. During the memory test, there were no significant differences in accuracy between the baseline and any of the error reducing techniques. Subjective evaluation of the participants' perceived effort also showed no differences between any of the conditions. The results of the user study led to several findings. The benefits gained from reducing errors using either command repetition or expressiveness reduction outweigh the additional costs of learning and using the new techniques. However, there is a limit to how much cost can be added before performance begins to suffer, such as in the case of the triple sequence condition. Once participants had the time to become familiar with using an error reduction technique, they were just as fast as without one. And when tested for their ability to memorize the commands, there were no differences in how accurately they were able to recall the commands. Lastly, our subjective measures showed us that participants did not perceive more effort when using either technique and felt that they were not more difficult to learn than the baseline. This work contributed new knowledge to understanding how novel techniques for reducing interpretation error can improve a user's performance with a noisy input mechanism. Our user studies showed that these techniques are not difficult to learn and can provide benefits despite the additional costs. We demonstrate the effectiveness of error reduction techniques so that designers can consider these techniques when developing a signal-based input mechanism. This study also lays the groundwork for possible avenues of exploration relating to the trade-offs of error reduction and increased costs to the user. Thank you for watching.